So welcome to the second segment of this module 2 on the power of randomness and the importance of probabilistic algorithms. Probabilistic algorithms, they play an important role. For instance, in case of distributed algorithms and networking, there are settings in which without probabilism we wouldn't be able to come to a solution. For instance, in a distributed network, if you want to do a leadership election and think of Byzantine agreement, then in that case, if everybody is using a deterministic algorithm, then it's impossible to come to some consensus or to some decision. So the whole system will end up in deadlock, everybody waiting for everybody else. An interesting application also that I like is the Ethernet network or the Aloha network. In case of Aloha, this is a communication network in Hawaii, and there is a delay, and this delay causes a problem because it means that your message you start transmitting, you can collide with somebody else. So in that case, what you do is, if there is a collision, both parties, both stations will stop and they will try again, but then with a longer expected time to next transmission, according to some well-defined probability distribution. And a more interesting case even is in the case of number theory. So let P be a prime number and let X be some number modulo P. Then we call y a square root of x if y squared is equal to x modulo p, which is the usual definition of a square root. But in this case, all arithmetic is modulo the prime p. Note that if y is a square root, then so is minus y, right? Minus y in this case means p minus y. You have to maybe reflect on that. And the algebra is rather simple. If y is a square root, then if you compute it minus y, the p's will cancel modulo p, so the result will be x. Now, it's a fact that if your prime is congruent to 3 mod 4, then there is a simple exponentiation that you can do to compute the square root y, and you need to understand this. One would need to understand Legendre symbols, and there's not something that is important at this moment. But the interesting thing is that if the prime is 1 modulo 4, then no deterministic polynomial time algorithm is known to compute the square root of y. So this is a specific case in which probabilism is important, because it is known that if we allow a probabilistic algorithm, then there is a very efficient algorithm to compute the square root. So this is another case in which the impossible becomes possible. There are also many cases in which we are using probabilism to improve performance. So quicksort is an example of this. Remember quicksort, where you have the pivots. You choose the pivots and you divide the elements along the pivots, and you do this recursively. So the choice of the pivots is random. Fountain code is another very interesting application. You divide a file into m blocks. Then each code word is a random linear combination of the m blocks. You can create essentially as many code words as you like. So the encoder can encode a lot of code words, and you spread them around, and it has the property that any subset of m plus e code words will allow you to recover the original with very high probability. So note that if you, of course you need at least m blocks to be able to decode. That's the minimal amount of information that's there. So E here is the excess. So it's the number of extra blocks that you would need. And so for instance, if you have like 10 extra blocks, then the probability that you cannot decode is less than 1 in 1,000. So this is very interesting, very cool application of randomness. Yet another example that I'd like to show to you. So suppose that we have a long string S and we want to see if there's a shorter string T. In this case, it's going to be the string university, if this is a substring of S. So now what are you going to do? You're going to interpret all the characters as some numbers, maybe in the interval between 0 and 255. And you're going to compute the sum. You're going to compute the sum of all the characters in the string university. And you're going to do, from the string S, you're going to take, in this case, 11 positions, and you're going to compute also the sum of the first 11 characters starting in position 0. Now, if the sums are different, then you are sure that university is not equal to S0. So you are sure that this substring is not starting at position 0. Then you can advance the S. I'm going to explain this shortly. If they are the same, then what you're going to do is you're going to do the real hard work. You're going to do the test character for character to see if the string is equal. Now, what are you going to do if you don't have success? Well, you're going to advance one position. So you're going to, instead of starting at position 0, you're going to start at position 1. Now this is a very simple computation, because you can take the existing sum, you can subtract S0, which is now dropping out, and you can include Sn, add Sn, which is now coming in. And so this will give you a very smooth way to compute S1. So this is the process, and you go on the similar for S1, S2 up till the end. So this is an interesting way to improve your performance, because now it means that you don't have to do all the comparison position by position. You start with checking whether these sums are equal. Now this strategy is also applied in different contexts. For instance, in the context of equality, if I want to check whether two strings are equal, I could do the same. I could use the function that I mentioned in the previous slide, just the addition modulo 256, or maybe I can use more advanced functions, because I have two strategies. If I use a not very good function, then I may have to do everything again. Or if I choose a very good function, then maybe I can accept the error probability. So, and this is essentially what we are sort of advocating in the context of this whole course. So we know this has been applied. For instance, a cyclic redundancy check, when a message is sent using the internet, there's usually a cyclic redundancy check. So the sender computes the CRC and adds it to the message. The receiver redoes the computation and check if the result is the same. If the result is the same, supposedly no error has occurred. If the result is different, then the receiver will suppose an error has occurred and will discard the message. And another context in which essentially the same idea happens is in the case of message authentication. You can think of Galois counter mode, which has also an additional redundancy check in which the error is 2 to minus 128. So I already said this. There are two strategies to deal with inconclusive heuristics. One is to do a rigorous test. If you are not sure that they for instance, they might be equal, or they might, your element might be contained in the set, then you do a rigorous test, or you accept the risk of a false positive by calibrating the algorithm to obtain a negligible error. And so in complexity theory, this one-sided error is known as RP, the class of randomized polynomial time algorithms. I'm going to give you yet another example, which is sort of my favorite example. It's on primality testing. So the Fermat primality test, what it does is the following. Suppose you have an odd integer n and you want to test whether it's a prime number or not. Now, if there's a theorem by Fermat that says that if p is a prime, then a to the power p minus 1 modulo p must be equal to 1. So we know that if for some a this equation is not valid, then we are sure that n is not a prime number. So indeed, in this case, we can even call this number a that doesn't satisfy the equality. We call it a witness. So this is a very interesting idea. You choose a random number modulo n. You're going to compute a to the power n minus 1. You reduce it modulo n, and you see whether it's equal to 1 or not. A problem with this test is that there are numbers that are immune to it. That means there are composite numbers that satisfy the opposite of this equation. So there exist numbers for which a to the powers n minus 1 modulo n is always equal to 1, even though they are not prime numbers. And so the Miller-Rabin primality test is an improvement on this. It has almost the same computational complexity, but it has a slightly more difficult mathematical background. But this improved mathematics allows us to get rid of the problems with Carmichael numbers, and it has very good performance. So this Miller-Rabin has the following property: a prime number n will never be declared composite, so would never declare a prime number to be composite, but a composite number may be declared prime with a very small, with a probability of 1 over 4, but if you repeat it k times, then it's 1 over 4 to the power k. So this will for choosing k like 40, this will lead to an error probability, there's a minus missing there, 2 to the minus 80. Okay, and so this is in practice, a very, very efficient algorithm. So let us reflect for a second on what negligible error means. So 2 to the minus 20 is about 1 in a million. That's the chance, more or less, to be involved in an airplane accident. Obviously, we don't want that. 2 to the minus 80 corresponds roughly to winning the Powerball lottery 3 times in a row. It's like this. It's like you take a lottery, and it's like you have to repeat winning 3 times, 4 times, 5 times. It's very, very unlikely. So there's this quote: in testing probability of very large number chosen at random, the chance of stumbling upon a value that fools the Fermat test is less than the chance that cosmic radiation will cause the computer to make an error in carrying out a correct algorithm. Considering an algorithm to be inadequate for the first reason but not for the second illustrates the difference between mathematics and engineering. And so we should reflect on this. We are in a process, we are in cryptographic engineering. It's also what I call the difference between mathematics and cryptography. In cryptography, we care about practical aspects. And this is certainly the case in the zero knowledge ecosystem. So if we compare this, the Rabin-Miller and this very small probability with the well-known AKS primality test, which is deterministic polynomial time, then what we see that unfortunately the complexity of this algorithm is somewhat on the high side, so in practice people prefer to use the Miller-Rabin test. And just to finalize with another example, I also want to mention Freifeld's algorithm, which is on the verification of matrix multiplication. So this is sort of what the area we are getting into. It's like the computation already has been done, but we want to verify it in a fast way. So given A, B, and C, we want to verify whether the product A times B is equal to C. And so what Freifeld's proposes is the following. We compute A times B times X and C times X for a specific value of X. The components, the values of the entries of X, they are either -1 or 1 randomly chosen. And then you compare the two results. Now we know that if the product holds, the equation holds, then for any value of X, it should be true. However, one can prove that if the equation doesn't hold, then with probability at least 1/2 in each round, you will find a different between A, B times X and C times X. So this is a very interesting algorithm. You can think of some variation of this algorithm. If the underlying set is the real numbers, you could even think of doing some of the tests modulo a randomly chosen prime P. If it's over the finite field of characteristic P, then you can even make a different choice. You can choose a random number R and use the xi's as the powers of R, and this will even give you a better a probability of discovering in the case that A times B does not equal C. So to wrap it up with some complexity theory, RP is the class of randomized polynomial time. So the essential thing is here in the case of RP, it's a one-sided error for all the X that are not in the language, the machine will always reject. And this is opposed to the class BPP, which is known as bounded error probabilistic polynomial time, which has a two-sided error. So the important thing to look at is that in the case of RP, there's only a chance of error here in the case when X belongs to L, whereas in BPP there is a chance on both sides. However, in both cases, by repeating the algorithm many times, we can get the error to be as low as we want. So here are some books on probabilistic algorithm. Known books are the book by Metzenmacher and Upfal, and the somewhat difficult book by Motwani and Ragavan, Randomized Algorithms. What I really like, I discovered recently, is this new book by Nick Harvey, first course in randomized algorithms, and you can find it online. I think it gives a gentle introduction into this highly interesting area. So that's it.